All right, so the next section we're going to cover is a really important area of chemistry called stoichiometry. And really what stoichiometry is it's the study of what's going into a reaction and what's coming out of a reaction. So it's the quantitative relationship between starting materials and products in a chemical reaction. And I'm going to abbreviate reaction there. So, for example, in this picture here, we've got one carbon atom reacting with one oxygen molecule to give you one carbon dioxide molecule. However, normally when we're doing chemical reactions, we're not just doing it with one individual molecule, right? We're doing it with billions or trillions or even more than that. So down below it says, all right, this same ratio is going to hold true even if you're using 1 mole of carbon atoms, right? So 1 mole would be 6.022 times 10 to the 23rd carbon atoms. That would mean you'd need 1 mole of oxygen molecules. So the ratio is going to be the same, right? So 1 carbon atom with 1 molecule is the same ratio as 1 mole and 1 mole, right? So 1-to-1 ratio, and then you get 1 mole of product out. You can also, from that, figure out how many grams you have, and how can we figure out how many grams we have? By using the molar mass, right? So yesterday we talked about how to find molar mass. So really it's just a bunch of math that you can use to convert between moles to atoms to grams, kind of like we were practicing yesterday. But there's a few really important things anytime you do this. So I'll show you the first thing. And that is to always balance your reaction. If you don't balance your reaction, you really can't do stoichiometry effectively. So this is arguably the most important step anytime you're doing stoichiometry. So let's take an example. And in this example, I've got SiO2. What would that be called? The silicon dioxide, right? We need to have the di prefix because this is covalent. And silicon dioxide is found in glass. So any glass, for the most part, has silicon dioxide in it. And you can react this with an acid called hydrofluoric acid. And hydrofluoric acid will actually eat glass, so to speak. And when this happens, you get a new product, SiF4. What would this be called? Covalent, it's nonmetals. It's a tough crowd today. Silicon tetrafluoride. And the byproduct for this reaction is going to be water. All right, so before we do any sort of math, we need to make sure that this is balanced. So for example, I could look at the left-hand side. I'd say there's 1 silicon on the left-hand side for our starting materials, 1 on our product side, so silicon looks good. Oxygen, though, looks like we've got 2 oxygens on the left and 1 on the right. So maybe I'll double this over here. That way I've got 2 oxygens on both sides. So now silicon and oxygen are balanced. Next, we would go over to the hydrogen and HF. And it looks like we have 4 hydrogens on the right, but only 1 on the left. So I'll put a 4 in here. So now we've got 4 hydrogens on both sides. And then last but not least, we check our fluorines, and it looks like fluorines are completely balanced. If you want, sometimes it's handy just to throw in a 1 here to keep track of, hey, this reaction is always going to be in a 1-to-4 ratio of silicon dioxide to 4 hydrofluoric acids, right? So we need to know that ratio. It's very important. Okay, so now we've got our balanced reaction, and we can do some math problems. Oops. So let's do a few easier ones. So problem number 1 is how many moles of HF hydrofluoric acid do you need to make 3.66 moles of water? All right, so we can set this up as a pretty simple math problem, right? So just like with any math problem, we always want to start out with what we know. We know that we've got 3.66 moles of H2O. And we're trying to figure out how many moles of HF are needed. So what I would do is first try to cancel out my moles of water. And we're trying to figure out how many moles of HF, so that must be our remaining unit. So I'd put moles of HF on the bottom, and now we've got to figure out what this ratio is going to be. How many moles of HF are there for how many moles of water? What do you think that ratio will be? If we look at our chemical equation, right, we've got 4 moles of HF for every 2 moles of water. So it's going to be a 4-to-2 ratio for those two elements of our chemical equation, right? So really quickly, we can plug this in and we can say, in our balanced reaction, our coefficient for HF was 4. Our coefficient for water is 2. So let's make a note that this is the coefficients from your balanced reaction. It just gives you the ratio. All right, so now when we plug this in, we can cancel out moles of water. Moles of water, we're left with moles of HF as our final unit. And that gives me an answer of 7.32 moles of HF. Does that make sense? So really we're just looking at ratios of reagents and products, or reagents to another reagent, or product to another product. All right, let's try another practice one. Oops, I don't know why that turned. There we go. Let's do problem 2 next. All right, problem 2 is going to be pretty similar. This one is how many moles of silicon tetrafluoride are made when 7.89 moles of water are made. So try to set it up pretty similar to our previous problem and use those coefficient numbers from our balanced reaction in your math problem. Does anybody think they got this one? A few people? All right, so let's try to do this together. Again, I always start out with what's given to us. I list that first. We're given the fact that 7.89 moles of water were made. What we're trying to solve, though, is how many moles of silicon tetrafluoride. So we need to cancel out moles of water. Put that on the bottom. And then I want to find out the moles of silicon tetrafluoride. All right, so now we need to figure out what number goes on top and what number goes on bottom. So I would go right back up to my balanced equation. Whoa. And I'd find my coefficient for silicon tetrafluoride, which looks like it's a 1, right? So I plug in 1 with silicon tetrafluoride. Plug that in, and then I'd go back up and I'd look at the moles of water, or the coefficient, which looks like it's 2 in our balanced equation, right? So then I would just plug in 2 down here with the moles of water. All right, when all is said and done, we've canceled out moles of water. We're left with moles of silicon tetrafluoride, which, let's see if I can do the math. It's like, what, 3.95? Okay. moles of silicon tetrafluoride. So without bouncing your equation first, you really can't do problems like this effectively, right? So we have to make sure that our equation's completely balanced, or else our ratios will be completely off. All right, let's do another one. This one's going to be a little bit trickier. All right, so problem 3 is asking about how many moles of water are made when 2.44 grams of silicon dioxide react. And I will give you a hint on where to start, and that is to convert grams of SiO2 to moles of SiO2 first. So I'll give you a minute to think about that. Remember, yesterday we practiced going from grams to moles and moles to grams, so you might need to use one of our unit conversions. Do you think you'll need to use Avogadro's number? No, that's only for converting between things and moles, not grams and moles. What do we need for grams to moles? Molar mass, right? So you might need to pull out your periodic table for this one. While you're working on that, I'm going to get us started with the molar mass. So for example, if I look at SiO2, I've got one silicon atom, which weighs what, 28.09, I think? And I've got two oxygen atoms, which weigh 16.00, which means this is about 60.09. So really quickly, I can come up with a unit conversion, and I could say 1 mole of silicon dioxide is equal to 60.09 grams of silicon dioxide, right? So that's our molar mass unit conversion that we'll need for this problem. I think we're in pretty good shape, though, to start. So let's go ahead and try to plug this in. And we could say, all right, we know we've got 2.44 grams of silicon dioxide. We don't want our units in grams. However, we can convert from grams to moles, which is what I gave you as that first hint. So let's put grams of silicon dioxide on the bottom and moles of silicon dioxide on top. So does the 60.09 go on the top or bottom? On the bottom, right? 60.09 was paired with the grams unit in our conversion. That goes with every 1 mole, okay? So now we've canceled out grams of silicon dioxide. We've converted to moles of silicon dioxide. But ultimately, the question isn't asking how many moles of silicon dioxide there are. It's asking about how many moles of water are made. So we need to convert from moles of silicon dioxide to moles of water. So let's try to do that. And we'll set up our math problem first. We want to cancel out moles of silicon dioxide. And we want to get to moles of water. All right, so now we've got to figure out the ratio for each of these. So what was the coefficient for water in our balanced reaction? It was 2. Okay, so we'll plug in a 2 here. That's our coefficient for water. What about for silicon dioxide? It was 1. All right, so now that we've done that, we've canceled out moles of silicon dioxide. We're left with moles of water as our remaining unit. And I'm getting 0.0812 moles of water. So we can convert from grams of one of our reagents all the way up to moles of another reagent just by doing multiple unit conversions in a row. That was why during the first part of this term, I was really trying to push unit conversions. It's easy to flip-flop these and put the 60.09 on the top. I always recommend that you write out your units, make sure that they're paired with the right number, and make sure everything's canceling when you're doing these problems. All right, I'll show you this simple road map. And this simple roadmap is pretty useful anytime you're doing stoichiometry. So let's say you're given the mass of some compound, we'll call that compound A in grams. First step I always do is convert that to moles, kind of the universal currency in chemistry. And then we can convert from moles of one reagent to moles of something else using the coefficients from our bounce reaction. And then once you figure out the moles of your other reagent or product, you can convert from that to grams by using the molar mass for that one. So in general, anytime you're doing stoichiometry, convert to moles first if you're given mass, then do a mole-to-mole conversion after that. So let's do another one. So let's do problem 4. And we'll stick with that same reaction because we've already bounced it. So how many moles of SiF4, the silicon tetrafluoride, are made when 12.3 grams of water are formed? All right, but try to use the roadmap as your guide. It's going to be set up pretty similar to the last problem, but with new and different numbers. If we look at our roadmap, it looks like we're given the mass of some compound A, and we're trying to find the moles of some unrelated compound. So for our roadmap, we're doing the steps in that red box, but we're not doing the last step, right? We don't need to figure out the grams of silicon tetrafluoride. They just want the moles of silicon tetrafluoride for this problem. Did anybody figure out what the molar mass is of water? Let's try it, right? So water has 2 hydrogens, which is about 1.01, plus 1 oxygen, and that oxygen is about 16.00. So I'd say this is about 18.02. So we can convert this and we can say, all right, 1 mole of water is equal to 18.02 grams of water. So that's going to be our molar mass unit conversion. All right, so let's try to set it up in a similar manner. We'll say, okay, we've got 12.3 grams of water. We need to convert that to moles. So what I'm going to do is put grams of water on the bottom, put moles of water on the top, and will the 18.02 go on the top or bottom? It's got to go on the bottom with the grams unit, right? Because 18.02 in our unit conversion was paired with grams. And we've got 1 paired with our moles. This allows us to cancel out grams of water, and we're left with moles of water. However, we don't want moles of water. We want moles of silicon tetrafluoride, so we need to cancel out moles of water in our next step. So I'll cancel out moles of water by putting that on the bottom, leave moles of silicon tetrafluoride on top. And if we looked at our balanced equation, what was the coefficient that went before silicon tetrafluoride? 1. It was just 1, right? So I plugged that in. What was the coefficient that went before water? 2. All right, so now we've canceled out moles of water. Whoops. Come on. 1 and 2. There we go. And now if we plug this into our calculator, I'm getting a mass of 0.381 moles of SiF4. Does that make sense? All right, let's do one more practice problem, and then I'll give you a more challenging one. And then if we have any extra time, I'll let you get started on your pod, which is just more practice. So let's do problem 5 first. And again, we're going to use that exact same problem. So this one is, what mass of water is made when 2.33 grams of silicon dioxide reacts? So this one might be a bit more involved, so I'll give you a minute to work on this. Yeah?
On the last one, did you say it was 1.8, or is this supposed to be 3, 4?
Is that my terrible handwriting? Yeah. I couldn't even read my own notes. You're entirely right. That's 3.41. My handwriting's awful, and apparently I can't read it some days. Let me just kind of give you a road map. So mass of silicon dioxide is where we're starting at. We're trying to get to moles of silicon dioxide. It's going to be our next step. And then after that, we're trying to go to moles of water, and then from there we're trying to get to grams, or mass of water, excuse me. Come on. So this first step, what will we need to know? We need to know molar mass of water. This next one, in order to go from moles of one reagent to moles of another reagent, you need to know the ratio of coefficients. From balanced reaction. And then last but not least, to go from moles of water to mass of water. Oh shoot, this one should have been silicon dioxide. I was getting it flip-flopped. The last one was where you need the molar mass of water. All right, so I'll give you a minute to work on this and then see if you're getting the correct answer from your neighbor too. All right, let's try to do this as a class. So we got to start out with our mass of silicon dioxide, which is 2.33 grams of silicon dioxide. Next thing we need to do is convert that to moles of silicon dioxide. So I'm going to say, all right, 1 mole of silicon dioxide is how many grams of silicon dioxide? Did anyone figure that out, the molar mass? What was that? 60.1, is that what you said? Yeah, about 60.09, 60.1, whichever one. So that's the mass of 1 silicon atom and 2 oxygen atoms. So now we've canceled out grams of silicon dioxide. We've done the first step on our roadmap, and we've gone to moles of silicon dioxide. Now we need to convert from moles of silicon dioxide to moles of water. So I'll put moles of silicon dioxide down here. We want to convert to moles of water. What's the ratio? What should go on top and what should go on bottom? We looked at our bounce reaction. What was the number in front of water? 2. Number in front of silicon dioxide? 1. So now we've canceled out moles of silicon dioxide. We've got moles of water. So we're on our second step. We've completed. Now we need to do our last step. And we want to cancel out moles of water and get to grams of water. And we need to have the molar mass of water, which we already found was 18.02. And does that go on top or bottom? Or go on top. It's paired with the grams. All right, so now we've canceled out moles, and we're left with grams of water. And when I type this in, I get about 1.40 grams of water. This is kind of the ultimate stoichiometry problem. Going from grams of one reagent to grams to another reagent actually requires a few steps, not just one step. Does that make sense? All right, so now I've got an interesting challenge problem for you. Let me get the problem started. There's a special type of mouse called a kangaroo mouse. I think they're found in the deserts of Nevada, kind of the southwest region, and they can actually survive without drinking water. They've evolved to live in these ultra harsh desert conditions where water is just not always going to be available, but they've adapted a way of surviving. And the way they survive is pretty clever. And you might remember this from our bouncing equations worksheet. C6H12O6 plus 6 equivalents of oxygen will create 6 equivalents of CO2 plus 6 equivalents of water. So if you remember, I said C6H12O6 was glucose. That's just sugar, right? So sugar plus oxygen, that's basically what you do when you metabolize food, right? You break down the carbohydrates in your body by inhaling oxygen. When you exhale, you breathe out CO2. And you also produce a little bit of water during this overall chemical process. All right, so it's a pretty unique system. This mouse has adapted so that the byproduct from this reaction produces enough water for them to actually survive. And they don't sweat very much. Instead, the way they get rid of their heat when they get too hot is through their big ears. So they radiate their heat out that way, they don't sweat. All right, so weird little mouse. My question for you is how many grams of water can be produced when 25.05 grams of C6H12O6 is metabolized. Let me clean up that 6. And I will give you a few hints for this reaction. The first one is 1 mole of C6H12O6 we found yesterday was 180.16 grams of C6H12O6. That's just the molar mass. And then we also said that 1 mole of water is equal to 18.02 grams of water. So these are the unit conversions you may need to use for this reaction. All right, just for the sake of time, let's try to work through this as a class. So we know we're starting out with 25.05 grams of C6H12O6. What's our first step going to be? Yeah, convert it to moles using molar mass. And I said that there are 180.16 grams of C6H12O6 in every 1 mole of C6H12O6. So now we've gotten rid of our grams of glucose and we've converted to moles. All right, now we need to start converting from moles of glucose to moles of water. So I'm going to put moles of C6H12O6 on the bottom. I'm going to put moles of water on top. How many moles of water do we get out for every 1 mole of C6H12O6 we put in? 6 from our balanced equation, right? So we get 6 moles of water out for every 1 mole we put in. So it's a 6-to-1 ratio. Okay, we can cancel out moles of glucose. There we go. We've got moles of water. Now we need to go from moles of water to grams of water. So I'd say, all right, 1 mole of water is equal to 18.02 grams of water. That allows us to cancel out our moles of water, and we're left with our units in grams. All right, so we figured out how many grams of water. Now all we need to do is type this into our calculator. What answer are you getting? 15.03? Exactly. So this mouse would get 15.03 grams of water out by metabolizing 25.05 grams of glucose. All right, I know this is tricky. Try to get started on your pod soon, and then if you are stuck, try to email me or stop by my office or get help. On Monday, bring your carbonates post lab. So that carbonates post lab we'll work on in class on Monday.